Okay, so the next section that we're going to talk about are related rates. The idea behind related rates is that we're looking at how can we apply derivatives to real-world problems. So that's the idea behind related rates. So the steps that we're going to do is we're going to try to take a word problem, draw a picture, label all of our variables, and then find the rate that we're looking for. So the steps to take, this first thing we're going to do is draw a picture and assign variables. So when we assign these variables, we're going to say in our problem what's changing, so what's varying and what's not. Anything that's varying we need to label with a variable. Then we're going to write out what we want to find. So maybe we're trying to find out the rate of change of volume. So maybe we're trying to find dV dt or something like that. We want to write out what we're trying to find. Third, write out what are we given. So in the problem, what variables are we given, what rates are we given, write all of those out. Third, find a relation. Find a relation between all of the variables and everything, or whatever you're trying to find. So find some sort of equation that relates them all, whether it be volume or the Pythagorean theorem or some sort of equation that you know. Find that relation. 5, you're going to take a derivative. Take a derivative. This is where you're going to introduce all the rates. So whenever you have this relation, there aren't going to be any rates in it. Remember, rates are found by taking the derivative. So what you're going to do is take a derivative in this step 5, and then lastly, we'll plug in and solve for what we're looking for. So for these related rate problems, this is the process that we're going to go through. We're going to first start by drawing a picture, if it's necessary, assigning variables. Ask yourself, what do we actually want to find? Then say, what are we given? Find the relation between all these, take a derivative. When you take this derivative, don't forget the chain rule. You're going to use the chain rule and implicit differentiation. Those are the two things that you want to be careful with when you take this derivative. Then lastly, we're going to plug in and solve. So let's just try an example. This is probably the most common problem with related rates. So this is a ladder is sliding down, I should say a 3-meter length ladder is sliding down the side of the house with the base of the ladder .5 meters away from the house. The ladder's base is moving away from the house at 0.25 meters per second. And I want to know how fast is the top of the ladder moving down, moving after 1 second. Okay, so a 3-meter tall ladder is sliding down the side of the house with the base of the ladder 0.5 meters away from the house. The ladder's base is moving away from the house at a rate of 0.25 meters per second, and I want to know how fast is the top of the ladder moving moving down the side of the house after 1 second. So let's go through these steps and figure this out. So remember, step 1, I'm going to draw a picture. So my picture here, I have a house. Okay, there's my house. Then I have a ladder that's against the house. So here's my ladder. And here's the ground. Alright, in this problem, what is varying? So as the ladder is falling down the side of the house, what's varying? Well, the height of the ladder here, let's call that x, that's varying. Also, the distance between the house and the base of the ladder, that's varying. The height or the length of the ladder, that's not varying. That's staying constant at 3. Okay, so we've assigned some variables. Next up, what do we want to find? The problem says how fast, that's talking about a rate, how fast is the top of the ladder moving down the side of the house after 1 second? So this is saying how fast is this moving after 1 second? In terms of our variables, what we're trying to find is dx dt. Right, we're saying how fast, so that's a rate of change with respect to time, how fast is this moving after 1 second? Let's write down what we know. In the problem, it says that the base of the ladder initially is 0.5 meters away from the house. So initially, it's 0.5 meters away, but we want to know after 1 second how fast is it. So we're not exactly, we can't just put in 0.5. We need to figure out what happens after 1 second. So after 1 second, how far away is the ladder from the house? Well, initially it was 0.5 meters from the house. It's moving away at a rate of 0.25 meters from the house. So after 1 second, y is 0.75. Okay, next, do I know dy dt? It says that the ladder is moving away from the house at a rate of 0.25 meters per second. So I know the rate of change of y is 0.25 meters per second. I think that's all the problem tells us. Again, after 1 second, the distance between the base of the ladder and the house was that initial 0.5 plus 0.25, because that's how fast it's moving away. The rate of change is 0.25. Now let's see. Can I find some sort of equation that's relating x and y? So let's see here. I know that x squared plus y squared is 3 squared. That's just from the Pythagorean theorem. So there's my relation. Now I'm going to take the derivative. Now when I take the derivative, I'm going to use the chain rule. Keep in mind, x is a function. X is not my variable here. T is my variable. Time is the variable. So if I take the derivative, I'll get 2x dx dt plus 2y dy dt is equal to 0. 3 squared is a constant. Taking the derivative of a constant gives you 0. Now I want to plug in. So let's see what we get here. I know that y was 0.75. I know that dy dt is 0.25. I'm trying to solve for dx dt, so I don't know that one. And I need to know x. Well, this wasn't given up here, but can we actually figure out x? Well, if I know that this is 0.75, I know this is 3, I can use my Pythagorean equation to figure out that this is going to be 3 squared minus 0.75 squared, and then take the square root. So that would be 2.9. So x here is 2.9. So what I was able to do here is find the relation, which was the Pythagorean theorem, take the derivative using implicit differentiation, then plug in everything that I knew. I had to solve for x, but that's okay. Now let's actually figure out what dx dt is. So I'm going to subtract this to the other side, divide by 2 times 2.9. Let's see, negative 2 times 0.75 times 0.25 gives me negative 0.375 over 2 times 2.9, which is 5.8. So I get negative 0.375 divided by 5.8, negative 0.06 meters per second. Now, does it make sense that the rate of change of x is negative? Well, it does, because the height here is decreasing. As the ladder's falling, this height is decreasing, so it makes sense that it should be negative. So the rate at which the top of the ladder is falling is going to be negative 0.06 meters per second. Okay, so let's try another one. Hopefully you can kind of see how this whole word problem thing is working. Let's say in a rectangular bathtub, water is being pumped in, at a rate of 0.5 feet cubed per minute. How fast is the water level rising if the base of the bathtub is 2 feet by 5 feet? Okay, so in a rectangular bathtub, water is being pumped in at a rate of 0.5 feet cubed per minute. How fast is the water level rising if the base of the bathtub is 2 by 5? So first thing I'm going to do is I'm going to draw a picture of this bathtub. So I have a rectangular bathtub. Okay, so there's my bathtub, not the best picture. In this bathtub, water is being pumped in. So for my picture, what is actually varying? Well, what's varying is the water level. So there's my water level. Let's call the height of the water level h. So h is measuring from the base of the bathtub up to the water level. What else do we know about this picture? Well, we also know that the base of the bathtub is 2 by 5 feet. That's not varying in our problem. The size of the bathtub is not changing. The only thing that's changing is the height of the water. In the problem, what are we actually trying to find? It says, how fast is the water level rising? So the water level is given by h. We want to know how fast, so that's a rate. So we're trying to find dh dt. What do we know? The only thing the problem tells us is that the water is being pumped in at a rate of 0.5 feet cubed per minute. Well, what is that? Feet cubed per minute, that's talking about the rate of change of the volume. So the rate at which the volume is changing is 0.5 feet cubed per minute. Now, how do I know this is the rate of change of volume? Well, I know that volume is measured in feet cubed, and this is per minute, so it has to be a rate. So it's going to be 0.5 feet cubed per minute. So I wrote down what I want, I wrote down what I know. Next, is there some sort of equation that relates these things. So is there some sort of equation that's relating volume, height of the water? What can we think of here? Well, how about the volume is equal to base times height. So the base has area 10, the height is h. So I know that the volume of water is 2 times 5, which is 10, times the height, so 10h. Now that we have the relation, let's take the derivative. So the derivative of volume, that's dv dt. Now what's the derivative of 10h? Well, the 10 stays. What's the derivative of h? H is not our variable. Remember, t is the variable, so 10 dh dt. And this is what we're trying to solve for. So now I'm going to plug in all my numbers. So dv dt was 0.5. I don't know what dh dt was. That's what I'm trying to solve for. Divide both sides by 10, so I get 0.05. And what is this being measured in? That would be feet per minute. So, what was I able to do here? I drew my picture, wrote down what I want, wrote down what I know in terms of rates, plugged it into the equation that I found, and solved. Okay. Let's say that water is being pumped into a cone-shaped tank. At a rate of 5 meters cubed per hour. If the tank has height 20 meters and radius 3 meters, how fast is the water level rising when the water is 10 meters high? Okay, so let's read this problem one more time. Water is being pumped into a cone-shaped tank at a rate of 5 meters cubed per hour. If the tank has height 20 meters and radius 3 meters, how fast is the water level rising when the water is 10 meters high? So let's draw a picture. So in this problem, I have a cone-shaped tank. So probably something like this, that's maybe up in the air. There's my cone-shaped tank. Now in this problem, what's varying and what is staying constant? Since water is being pumped into this tank, I know that the water level is changing. So there's my water in blue. Let's call this h. Let's let h be the height of the water. Now, what else do I know here? Here's my h. Also what's varying is the radius. So the radius at this water level, let's call that r. What's not varying? I know the height of my tank is 20 meters, and I know the radius of my tank is 3 meters. So I think that's everything we know. So in this problem, not only is the height of the water kind of changing, but also the radius. And that's because the volume is dependent upon the height and the radius. So what do we want in this problem? The problem says, how fast is the water level rising? So in terms of this problem, we're looking for dh dt. So the water level is given by h. How fast is it rising? That's the rate of change. What do we know here? Well, the problem says that the water is being pumped into the cone-shaped tank at a rate of 5 meters cubed per hour. So that says the volume of water is changing with respect to time at 5 meters cubed per hour. So I think that's the only one that I know at this point. Okay, so now what could I do? I want to figure out some sort of equation that's relating height and volume. So how could I do that? Well, the volume of water that's in here is pi r squared times the height. So pi r squared h. The only issue is, how are you going to take the derivative of that because you have two variables? So to get rid of one of the variables, you're going to have to use the fact that it just can't be any radius and any height. It has to kind of match up with this triangle. So to figure out one of the variables, we'll set up a similar triangle. So we'll say that 3 is to r as 20 is to h. And now let's solve for r. So if I solve for r, I'll get, what, 3h is 20r whenever I cross multiply. So r is 3 over 20h. Now I can plug that into my volume. So I'll get pi r squared here is going to be, what, 9 over 400 h squared times h. So I plugged in r for r squared. So this is 9 pi over 400 h cubed is equal to my volume. So again, what had to happen? What we're looking for is the volume of water. The only issue with the volume of water is that the volume is dependent upon two different variables. It's dependent upon r and h. So we had to kind of solve for one of the variables in terms of the other. We did that by setting up similar triangles. So the two triangles were, if you want to draw them on a picture here, this first red one and then this second red one. So I compared the big radius to the small radius, big height to the little height, solved for r and plugged it back in. So this is the equation we want to take the derivative of. So the left hand side, derivative of volume is dv dt. And now what about on this side? Well, remember that h is a function, h is not my variable, so I'm going to have to use the chain rule. So this will give me 27 pi over 400 times h squared times dh dt. Oh, we didn't write this. In the original giving part, they told us that the height of the water is 10. Now just plug in everything. So 0.5 is 27 pi over 400 times 100 times dh dt, and let's solve for dh dt. So to do that, let's see, what is 27 pi? So 27 pi divided by 400 times 100. This number here is 21.2. So I'll take 0.5 divided by 21.2, and I get 0.024 meters per hour. Hopefully I did the math right there. So again, what did I do here? I just plugged in plugged in my 10 for h, plugged in my, oh, it should have been 5, should have been, not 0.5, 5. 0.235. Plugged in my 5 for dv dt, plugged in my 10 for h, solved for dh dt. So that's what I was able to do to find the rate at which the volume is, the rate at which the height of the water is increasing. Let's do one more of these that involves an angle. Let's say that a firework leaves the ground vertically we have a camera sitting 100 feet away from the firework, taking pictures. At a certain moment, the angle between the firework, the camera, and the ground is pi over 4. And that angle is increasing at a rate of 0.1 radians per second. I want to know, what is the velocity of the firework at that moment? Okay, so kind of a longer problem here, but basically a firework is leaving the ground and it's going vertically. We have a camera sitting 100 feet away on the ground and it's taking pictures. At a certain moment, the angle that's created by the camera, the firework, and the ground is pi over 4 radians, and that angle is increasing at a certain rate. I want to know how fast is the firework moving. So let's draw a picture here. So maybe here's the ground, here's my camera. I have a firework that's kind of leaving the ground and traveling vertically. So there's the picture. I have a firework that left the ground, goes straight vertically. I have a camera sitting 100 feet away. So in this problem, let's ask ourselves, what is varying? What is staying constant? Well, one thing I know is I know that this distance is going to remain 100 feet. The camera's not moving away from where the base of the firework was. I know that that camera's staying still. They're also talking about the angle between the firework, the camera, and the ground. So let's see, here's the firework, here's the camera, and there's the ground. So I know this angle theta is also varying. Do I know anything else that's varying? Well, the firework is going higher and higher, so I know that's changing. Let's call it h. So in this problem, we're talking about an angle, we're talking about the height of the rocket, or the fireworks. So here's my picture with all the variables. What is the problem asking for? It's saying, what's the velocity of the firework? Well, that's talking about the rate of change of the height. So we want dh dt. What do we know? Well, let's see, the problem tells us that the angle is pi over 4 radians. It also says that the angle is increasing at a rate, so that's talking about d theta dt, 0.1 radians per second. I think that's all we know. Can I think of some sort of relation between theta, this height, and this 100 feet? Think about your trig functions. What function is going to relate theta, h, and 100? Given that this is a right triangle, I know that tangent of theta is h over 100, which I'm going to write as 1 over 100 h. Now that I have my relation, let's take a derivative. Remember, h is not my variable, t is the variable here, so I'm going to have to use the chain rule. So the derivative of tangent is secant squared. So secant squared theta d theta dt. And what's the derivative of 100h? Well, the 100 will stay. And then by implicit differentiation, I get dh dt. Now I'm going to plug in and solve for the dh dt that I wanted. So theta was pi over 4, so I'll get secant squared of pi over 4 times d theta dt was 0.1 equals 100 times dh dt. Continue this up here. So let's see, secant squared of pi over 4. Secant is the same as 1 over cosine. Cosine of pi over 4 is square root of 2 over 2. So if I square this, I'm going to get square root of 2 over 2, so 4 over 2, which is 2, I do believe. So I'll get 2 times 0.1, which is 0.2 2. So again, 1 over cosine of pi over 4 is 2 over square root of 2. Square that and you'll get 4 over 2, which is 2. 2 times 0.1 is 0.2. Now multiply both sides by 100, so I get dh dt is 20. And that is 20 feet per second. Because height was measured in feet, t was measured in seconds. Okay, so these are 4 problems just to kind of give you an idea of all the different types of related rates that we could look at. So just go through the process of drawing the picture, writing out your variables, what do you want to know, what do you know, finding a relation, take your derivative. Don't plug in numbers until after you've taken your derivative, and then solve for whatever you want.